Okay, so ooh, okay. So there's so the main results that we proved is that equal to unitary is some base plus rotation and the control. If you have bunch of control, but the target is just one unit, one single unitary that you can decompose with multiple to qubits. Not just not you don't need arbitrary to qubit. You only need one so-called CNOT and plus single qubit unitaries. Oh, so with these tools, then we can ask what about the general unit terms, right? The general 2 to the n times 2 to the n unit terms. All right, so before we go into this, we need to have some definition. Okay, so these are like people always talk about. These are like some terminology. So first is called universal gate set. So what is this say that what is universal gate set means that there is a set of gates which we can compute any unitary operation to the arbitrary address. So that means that if you give me unitaries, I can come up with bunch of sequence, which you, maybe it's not maybe you cannot easily find the sequence, but there exists a sequence of unitary in this case set such that you can approximate, you can approach to your unitary to arbitrary address. Okay, so classical analog is basically name gates. Name gate is classical universal for classical computation. By the way, public gate is name gates. Public gate is universal for classical computation. Maybe it's not easy to see, but let me just write down the why. So remember the definition of public gate exactly, right? So you have it here. And then you have this, right? These are public gate. If these are all one, then you apply this, right? Then let's say this is A and B. Let's say you forget about this. You forget about the content is you're working with the classical. Let's say this is A, right? B, A and B are either 0 or 1, right? In a classical circuit. And then you put 1 here. Then this is still A, this is B, right? But what is this guy? Well, what is this guy? So if A and B are all 1, then this 1 will get flipped. So that means that this is 1 plus A times B. Right? If A is 1, B is 1, this is 1, which is you get 1 plus 1, which is 0, you flip. So this is N, right? And then you flip with 1. So this is N. So this is NAND gate. You forget about these two, you get NAND gate. So public gate is exactly the same as NAND gate as a classical computation. So hopefully it's obvious. Oh, so the classical analog basically say that public gate is universal for classical computation. Okay, so this is the final result that I hope you here. It's basically what it says is that actually hotline space S and C9 I will get T are actually completely different. This is the final results that I hope. So notice that it's infinite. You only need 4, actually 3. Okay, so to prove this whole to prove these results, we need to do step by step. So the first basically 3 steps. So let me just talk about the first step. So this is the one that's maybe going. So now let's say we're working with the general 2 to n times 2 to n. It's a general d by d unitary. You forget about all these results that we proved. Let's say somebody gives you a d by d unitaries. My claim is that you take any d by d unitaries, you can decompose these d by d unitaries by using so-called 2-level unitaries. So that means that 2-level unitary means that there's a unitary. You can use this is unitary, but it's large, but it actually it actually only apply on the small two level. That means there is a contributor A, B, C, D, and the rest are all one. One. It apply on small. It only apply on small two levels. So for example, C naught is the two level unitaries, right? Because I can build a C naught right as a matrix is it is a small corner. The rest is the same as identity. This is the definition. Alright, so simply speaking, a two-level unitary is X naught trivially are at most two computational basis. Is the definition. Okay, so the claim is that if take any p by the unitaries, I can decompose it into two-level unitary. Why this is true? Okay, so we need to we do some examples. Okay. Okay, so let's say we do like three by three unitaries. Someone give you this have that you take for these three by three unitaries. Okay, and suppose I can find the two-level unitaries U1, U2, U3 such that these three times U is identity. That means that I can write U in terms of one dagger, U2 dagger, U3 daggers, right? And the dagger are also two-level unitary. So how can I find U1, U2, U3, which is only two level? Okay, so let's see. Let's see this speed. Let's see. So there are two cases. The first case is B is 0. Okay, so if B is 0, then let's say I pick U1 to be identity. Okay. If B is not 0, then I pick U1 to be this. Oh, you know, so what are you going on? So let's say. So if B is not 0, then I pick U1. Okay. So you can see this what this U1 is takes the submatrices A, B, let's see, let me just write down. Right, so you see this A and B, right? Here. So this U1 is defined with this. This is a unitary, right? Basically, this is one, so this is basically about some rotation, no second rotation. This is unitary here. And what the goal for this U1 is that we hope U1 times U will make B 0. Will make the original B here. Okay. So why it's true? Just quickly do it. Okay, so this is weird, but it's very simple. You don't care about this, right? And then say you want, so basically simple, you try to find a unitary such that once you do the matrix product, then these guys. So what is choose is basically A star and B star minus B and A. Right, so the important part is this B minus BA, these are 0, 0. Right, so when you times these 3 by 3 matrices, let's say I only care about this guy, this position. So it's this position. Right, so what this position here is basically this as this. Right, so it's minus B times A plus A times B. So what you do? So what is U1 is very simple. You just pick. You forget about all this normalization constant. You just need to pick B and minus A. So once you pick B and minus A and 0 here, then U1 times original U will kill this position. And once you pick B and minus A, then you need to normalize, right? Because any 2 by 2 unitaries, remember that the norm of this factor need to be 1, and this need to be 1. So we need to first normalize, and then if these two need to be also multiplied. So that's why you pick A star and B star. So it's very simple. You forget about normalization, you pick B and minus A, and then you need to add normalization factor. So it's very simple. You just try to find a unitary U1 such that it kills this off diagonal 0. Per se. Okay, and if B is originally 0, then you don't You just pick U1 to be identical. Okay. So similarly, right? Then you just need to. And second step is that I want to kill this guy. So it's very simple that we do a similar thing, right? So if C prime is 0, then I don't go and if C prime is not 0, then I do the same thing, right? Just do a C prime minus A prime, kill with this guy. Similar reason. Right? So once I pick this, okay, so there is this, then I can kill this. Then I can kill this. Okay, so notice that once I do this, right? So once I do this, then what's the remaining matrices? So when I do U1, U2, U1, and U, then whatever it is, right, it already becomes 0, 0 here. Right. But the problem is that this guy is also unitary. So in order to make this guy to be unitary, this guy need to be this must be a unit vector, right? This whole matrix is unitary. So the first column must be a unit vector. So there must be a number here, let's say x. Then this number must have magnitude 1. But since it's unitary, right? So this row also has magnitude 1. So this force, these two must be 0. So that means and you can pull all x. You can take extra base. If you take extra base out, right? So that means that once you kill these two to make these two to be 0, then the remaining matrices must be written as the number here, now 0, 0, 0, 0. And you can normalize, you can take out extra base to be 1 and you get something. So these are 2-level unitaries. So that means that once you test it, you can take additional U3 to be whatever here. Like 1, 0, or something here. So that means that you find factorization. So U1 is 2-level and U2 is 2-level, U3 is 2-level. So it's make the definition possible. Okay, so if you believe so if you are convinced by this 3x3 story, then it's simple to generate the arbitrary d by d, right? And then I give you d by d. Then you can find the 2-level unitary to make this guy 0, this guy 0 is 0 Then the remaining, once you times the small 2-level unitaries up here, then the remaining, let's say, must be 1, and these are 0. Then you can apply this story on the rest of this guy and say that, oh, this is 0, I times a small unitary 0 here. And the story just since these guys are unitary, so this must be 1, these are 0. And then let's make a story, then you just keep the composition. So after, so hopefully you are convinced by this proof. So for d by d unitary U, you can first find U1, U2 up to d minus 1, which is 2-level unitaries. So remember that 2-level basically means that there's a only x on the 2 computational bases. Such that this U d minus 1, U has 1 top left and 0 else in the first row in column. As I just got here. And this will take you d minus 1 unitaries 2-level to kill d minus 1 of diagonal element. And you do it again, right? You do repeat this algorithm for d minus 1 times d minus 1 something. So finally, after 1 plus 2 plus 3, after 1 plus 2 plus 3, up to d minus 1 2-level unitaries, then the remaining is another 2 unitaries. So it's spent like d times d minus 1 divided by 2 2-level unitaries. Then this huge unitary is decomposed into small 2-level unitary. So this is the okay. So now what we have done is that so any unitary, right? Any d by d unitaries, whatever it is, it can be decomposed into a product of small like two-level unitary. So two-level unitary just apply. You can view these two unitaries apply only on two level, right? So it looks like a single qubit unitary. But the problem is that this single unitary may not be directly as a single qubit on particular qubit. So for example, right, let's say for example, let's say d equals 3, then this two-level unitary may look like, oh, it may be some like, or maybe let's say d is 4 or something, it may be some two-level, but apply on some weird, let's say 1, 1, 0, 0 basis, or like let's say 0, 0, 1, 1. So there may be if you apply on let's say d equals to 4, there will be some unitaries which is two-level, but apply on these two bases. But these two bases are not a single qubit, apply on particular qubits that is mixed up. Right? You mix up 1, 1, 0, 0, 0. So it's not a single, it's a two-dimensional subspace. Right, but it's not a two-dimensional subset particular that fix our qubit by remaining of some one single qubit. So this is the final thing we need to fix up. So the idea is that if you got something like mix up, then you can use the control unitary to fix this. So the next step is that so what this theorem tells me that I only need to deal with two-level unitaries. And once I solve this, once I decompose these two-level using some control operation, then I can decompose this control operation using C naught again, and then I prove this. Then I can factor everything into a single qubit plus C naught. Oh, okay. So this is the okay. Hopefully, it's the last two steps. Oh, so arbitrary unitary on d-dimensional Hilbert space and then product level unitaries that we just proved using the. So the goal is to show that a single qubit RCR can be of any two-level unitaries. This is the goal. Once we prove this, then we prove that any d-dimensional Hilbert space can be used and using the single qubit gates and CNOTs. Once I prove this, right? So combining, if I prove here, then I can prove that single qubit and CNOTs are universal for quantum computation. Once I prove this two-level guy can be solved. Okay, so the proof is the mathematical proof you can see the textbook. It's a somewhat complicated thing. So it's the same proof that so I will use one example, and once you understand the example, then hopefully you believe the general proof. So the proving we need to first using the so-called gray codes. So what is gray code is simple. I give you two binary strings. What you call S. You can do it as a source string, and the T is the target. You can define a so-called gray code, which is a set of binary strings which only from S to T, but each time only change one position. So for example, let's say S is 1, 0, 1, 0, 0, 1, and T is 1, 1, 0, 0, 1, 1. You want to find a path from S to T, but each time you can only change one bit. You see on this. So for example, this is S, right? 1, 0, 1, 0, 0, 1. Let's say I change the fifth one, right? So I change this 0 to be 1, so I get 1, 0, 1, 0, 1, 1. And after that, I flip the third bit 1 to 0, so I get 1, 0, 0, 0, 1, 1. Then I flip the second bit to 1, so I get 1, 1, 0, 0, 1, 1. So these gray codes are very simple. You start with S and T, but you only differ in one bit per step. You can prove this is always exists, right? But you start with one string, another string, and you just flip one by one. And you can change. And obviously the length of gray code is less than the number of n plus 1. Because n is the length of bit string. Because there are both n bit string, right? So the largest step is that you just remove, you just flip everything. You start with all 0 and go to all 1. Then you need to spend like n plus 1, right? Okay.
Then how can n be equals to n plus 1?
Oh, because you need to count the start and ends. You start with all 0 and go to 1, as if you do 1, then it takes more steps. Because you need to count the initial and the final. So that's fine. So yeah, so so let's say now I consider a two-level unitary U, apply some configuration of state S and T, then I construct all these variables. Okay, so now the magic happens. This is what people develop. Okay, so this is somehow the algorithm, but let me just using this as an example. Using example. Let's think about the n equal to 3, which is the trivial case. Let's say U apply on 0, 0 and 1, 1, 1. Right? So this is not single unitary because it's not computation, it's not our Pythagoras cube, right? It's fixed all 0 and 1. So if you write these matrices A by A, it's basically A and C and B and D. So these two unitaries are A, C, B, right? But if you write in terms of A by A matrix, it's basically not as simple as the standard unit. Okay, but now let's say I construct the variables. Start with all 0 and go all 1. Okay? I go 0, 1, 1. So how can I decompose U using this usual? How can I do this A, B, C, D using this? Okay. So what this circuit basically will swap 0. So let me just write on. Let's see the circuit. Okay, so this is the circuit. Oh, so let me just call. I will go through the. So actually, if you okay, so if you don't use the example and only using the math, then it will be like very difficult. But yeah. All right. Yeah, we don't need to work. So in order to prove this, we introduce another small variance of control dot. We call it that this is a white this is white here. So this is as similar as control dot, but it will flip the target if the control is 0. So this is just very convenient. And you can construct, you can prove, you can develop the circuit by using the original C naught by just adding the 2x here. Right? Because when you put extra x here, it basically is the same as you flip this. So this is just a simple additional okay. 我就讲，就是为了要让这个证明顺利，我们就定义一个奇怪的东西，这东西就是跟 C 纳的一样，我这边画了白的，意思就是说这个是0的时候才会翻过来，这样。那么 so exactly the same as C 纳 but you will flip the target bit if the control bit is 0. That's it. And you can prove that this guy can be constructed by using X and C naught. And because you can just sandwich X here, so it's the same as if this is 0, then you will get 1 anyway.
Actually, I have a question because we are talking about it being 1 or 0 all the time.
Yeah.
Why can't it be a linear combination?
Oh, it's fine. We only care about basis, right? If the basis is the same, then we just extend linear.
Okay, so actually but what about whether the is going to be carried out then.
Yeah, this is what I'm talking. Yeah, so I will talk about. If you see these demos, yeah, you can.
Because we defined the U not gates, like the control U gates,
Yeah,
as the control bit needs to be 1 and then we carry out.
right.
Right. So
Right.
what if our control bit is a linear combination of 0 and 1? Do we then?
Then you just extend
linear
linear.
combination as well?
Yeah, linear extend linearly.
Okay, yeah, that's.
So hopefully everybody understand what is guys. Okay, so let me explain this a bit. So what is the first case here is y control. So this means that if A and B are all 0, then this guy will be fit. And the second guy is flag control, flag target, y target, and the flag. Meaning that if this is 0, this is 1, then this will be fit. Otherwise, then nothing happens. And the final guy here is basically single group unitary, and that basically means that if this guy is 1, this guy is 1, then you will apply U2. Okay. Okay, and the right hand side you just copy from that. And the reason is very simple because you need to undo this extra. Yeah, you basically need to undo it. Okay, so my claim is that. So remember that this U tilde. So remember the goal. What? So what's the goal? So the goal is that this two level guy U only acting on 0, 0, 0 and 1, 1, 1 non-trivial. So for any state which is not 0, 0, 0 and 1, 1, 1, it should be trivial. It should be acting linear, acting identity, right? So my claim is that if you take a small U tilde as a single qubit unitary here, apply on the first qubit, then this circuit only acting non-trivially when the input is 0, 0, 0 or 1, 1, 1. Why this is the case? So let's see. So I will do it again. So I will do it once, right? So let's say in order for this U tilde to be applied, right? This guy and the third and this guy must be 1. Right? So this must be 1. Let's say if U tilde applied. Then third guy 这两个是1嘛？因为这两个是1，这个 U tilde 才会出来是第一个。Okay, so if this guy is 1, then this guy must be 1. Right? This is 1, this is 1. If U tilde applied, then this guy must be 1. This guy must be 1. But there's no control. This is control, but there's no target here, right? So this must be the same. So 1 must be here. Okay, so now there are two cases. There is a case that this guy, this control, this target will be activated or not. Let's say let's say this guy is activated. So that means that before this net will be 0 because it activated. Okay. If this is activated, that means that this must be 0. So that 0, white and black will activate this. So that means that. Okay. So, but this is all black, right? There's no target here, so this must be 0, 0. But now if these two are 0, then the first gate will be activated. So C must all be 0. So if U is applied, then the initial must be 0, 0, 0 if the middle guy is activated.大家可以回去看这个，想一下这个过程。其实这个很痛，对，好，其实不讲这个。 这就是讲一些一般的国家。So this is the first case, right? And the second case, let's go back to the mean. Let's forget about this. Okay. So we go back to the middle step, right? So let's say let's say the second gate, the second set, this middle guy is not activated. It's not activated. Okay. That means that the middle one can pass here, right? This guy must be one. But if this guy is not activated, but this guy is already one, right? So this flat condition is already satisfied. Then this guy must be one. Otherwise, then this white one will be activated. So this must be one. And if this is one, this is one. If this is one, this is one. And these are black, and these are white, right? So this will not be activated for this. So what these three circuits, what this set tell you is that if U tilde apply, then the initial state must be 0, 0, 0 or 1, 1, 1. Okay. 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 So now the rest is simple. Let's say the initial state is a 0, 0, 0. Okay, let's say. So what I'm saying is that if U tilde apply, then the initial must be 0, 0, 0 and 1, 1, 1. Or 1, 1. And if you write down everything in detail, then this you can show that this U tilde actually serve as previous U. Because these three, all these guys, only acting on trivially on 0, 0, 0, 1, 1. So all these guys can be viewed as a unitary only acting on these two computational bases. So it must be, if you pick U tilde of A, B, C, D, you will apply S, what you think, apply on these only two bases. So finish it. So why? Because now, so finish it. Okay, so if you believe these gray codes can be applied for arbitrary n by n, you can see it's very simple. What is our let me just talk about it. So remember you start with 0, 0, 0, right? And 1, 1. Now you apply these gray codes. So these gray codes will only flip it. So let's say this is the gray code that I use, right? So the first, if I start with 0 to go 0, 0, 1, then start with that, and that means that I put 0, 0 and control with this. And if I go to the next step, this guy, then I use these two to control with the target one. So hopefully now you can see how these gray codes match with this circuit. Each time you flip a bit, right? You flip. So the gray codes will only flip one bit at a time. So by this, then the position that this gray code flip is exactly the same serve as a target that you flip, right? So you can see 0. So you flip the third one and flip the third one and the second one. So you flip the third one and then flip the second one, you can use 0, 0, 0, 0, 1, 0, 1, 1, and you match with this. So this is how this design. This is some people try to develop. And if you go to the textbook, the textbook has this. You just write down the source and target, and you can using the control with flip on the where GI plus 1 differ, and then apply. So if you just see that these algorithms are very difficult. So that's why I talked about example first. Okay. You can go back to the textbook and see. And you need to do this. You need to undo the. Yeah. So there's a detail. A small detail here is that. all these control qubit, their square equals to 1, right? So these two, if there's no loop here, then if there's no loop here, then this guy will be identical. And then these two square will be 1, and these two square will be 1. So if you tilde, if there's no u tilde phi, then all these circular are identical. Because you apply the control twice, then you get original. You get identity. Because if these are you flip this, then you flip again. If there's no u tilde phi.
So the operation is also the same.
Yeah. So that means okay. So okay. So hopefully you believe that we can implement. So let me just write down the logic. Oh, okay. So
is the reason that we are doing this because we assume that we have some system where maybe due to space constraints we cannot just apply a gate onto bits that are away from each other? What I mean, because why are we doing all the difficulty of rearranging?
No, I mean so I think the now technology. Yeah, so a part of I think what you're saying here is that I gotta go down read it, but the technology now is that we cannot do like it's very hard to do like 3 qubit gates. So the technology now is that we can more or less do like 2 qubit gates. But for 3 qubit it's difficult. So we hope to like factorize any unitary using single qubit and 2 qubit.
Yes, but what I mean is why are we doing these steps? Why are we not saying we're already done? Because in every step we are going to apply one unitary matrix operating on qubits, and then we just input the right qubit like if we just have them on the row.
No.
Okay, well, let me think about it.
Okay. So what we have done is that you first have this general like d by d, where d is that 2 to the n, 2 to the n. So the first step, what we say is that this u can be if you break a product of level, and using these square codes tell you that this to level can be done by some many control u, many control with C naught the X gate, as is right here flip. So many n minus 1 n plus single qubit unitary single u. But my previous results, my previous tool tell me that arbitrary Cn minus 1x can be decomposed using the C naught plus a single u. So that means that you combine with these three, any d by d n 2 to n times d 2 to n matrices can be done by product of C naught plus single u. So this is the whole proof.
I get it. Okay.
Yeah, okay.
You're doing this for the step from the 2 level.
Yeah, 2 level unitary, and then you do that. So this is the whole proof. If you see the textbook, it spent like I don't know, maybe 50 or 60 pages. But yeah. So implement 2 level you require let's say OS square single qubit and C naught 2 n minus 1 is fine. Yeah, you don't need to understand. This is just some. This is the oh, by the way, this is not the optimal way to compose. This is just some textbook method. And after like along like this years, there are various ways that people try to find the best way to decompose. Okay, and so the total complexity is that from this method you can produce n squared times 4 to n gates. So this is exponential but sufficient for universality. Right, because you need exponential to level. because you need this square two angles, right? And then this guy also. So this is linear. This is linear. Okay, so everything we want to prove spend like to prove that exactly universal. Exactly universal means that can be so you can so this you will these are not approximate, right? These are mathematical equal sign. So this is it's so this is why it's so exactly universal. Can be decomposed as single cubic unitary plus C naught. 所以这个就是说，这个就是说，这个量子工程，这个 quantum computing 是可能的，因为你不需要做出任何的 unitary 嘛，你只需要 single cubic unitary and C naught. You don't need arbitrary unitary. You only need a single cubic. All the single cubic unitary and C naught would be enough to give you exactly the universe. Okay, but we are not done. The reason is that single cubic unitary are still uncountable, right? So we have not done to we have not solved this because we need to do only finite element in the lab. We cannot have the continuous element in the lab. So we need a so-called discrete universal case. So this is the next stage. Oh. So single unitary are universal but not able to decrease because they are continuous. So the final theorem, which is proof what I want to prove is that there exists a so-called discrete case set. Discrete meaning that you have only finite. So I will prove it to you is that actually you only need alpha, C naught, and T. So there are only three are enough. And you may, oh, how can that be? Right? Oh, but the problem. Okay, so now because single cubic and C naught are enough, right? So C naught 2 cubic unitary, there are only one of them, so it's fine. We don't care about it. We don't care about how can I decompose a single cubic unitary to find that one. Approximate single unitary to be find that one. So this is the last step. Okay, so let me before I go to proof, the idea is basically as I showed that single cubic unitary can be decomposed using the orbital angle. Right? So I only need two axes. I only need two axes, two non-parallel axes. So as long as you give me some. So you need to give me, like, let's say I take one single cubic unitary that represent one axis. And then you give me, let's say two single cubic unitary. One is axis, the first axis, one is the second axis. As long as they are non-parallel, then there may be a chance that I can do a general rotation. So this is the idea. Okay, so this is why we take Hardeman in T. Okay, so let me just describe what the hell is going on. So okay, so first let's say I give you this T. I give you this T, which is pi over A. Okay, so by definition, you can prove this T is a rotation by pi over A, known as Dx. This is the definition. Okay. And so I have one axis, which is Z, right? But in order to using this orbital angle theorem, I need to have another axis which is parallel, not parallel. It's not which is not parallel to Z. Okay, so this let's say I take so-called Hardeman case, which I conjugate with T. Okay, and as I say, is that Hardeman will change Z and X. So if you have Hardeman gates, you sandwich with the T, then you get rotation by pi over 4 of X. You can use the X as well. Okay. And yeah, this is some calculation that you don't need to do it, but you just try to calculate this. Just try to. Okay. Okay. But now, okay, so now if you believe what I'm saying true, that okay, you have one t gives you some angle, right? And the one another alpha sandwich of t gives you another axis, another two axes. But what about angle, right? In order to do this Euler theorem, you need to have continuous angle. Now you have two axes, but it's fine. That's fine. But how about angle? 对吧？你现在有两个不同，你要使用这个任意的旋转可以被写成是两个转轴跟三个欧拉角，对吧？那你现在已经有两个转轴了，对不对？那你现在可是你有三个欧拉角，欧拉角是零去，对吧？你不能说你只能转派除以8，对不对？那万一别人派除以3的，所以你要解决这个问题。Okay, so the remaining is that how can I deal with the continuous angle, which is a problem. And okay, so this is the theorem that it's very difficult to prove, but I will tell you the theorem. So this is a mathematical theorem called average distribution theorem, which is group 5. So this is a typical number series theorem, which is it's actually not related to quantity. Oh, it's related to quantity information in this content, but the proof is very difficult. It's not a complete. If you give me 1 hour, then I can try to. What this theorem tells you is that if you give me an irrational number, I compute the multiple of irrational number, mod 1, then it's uniform distribution of circle. 大家知道在说什么？就是说，okay, so let me explain. So, by the way, I mean you don't need to understand this. This is just funny, just funny thing. So, so if you draw a circle, right? If you draw a circle here, or maybe and you plot the maybe let's say so maybe I say if you take for example like exponential to pi I with the square root of 2 and times n cube. If you do something like this, then you take n to be integer. Right. So if you plot on a circle, then you'll get this, get here, get here, get here, get here. If this number is irrational, then there's no period, right? If let's say this is for example, if this is rational, it's a p over q, then if n is multiple of q, then you will go back to origin.
So is mod 1 saying you take the absolute value of complex number and then you divide it by its?
No. So the mod 1, so the mod 1 basically just take the. No, the mod 1 just take the other chain. You remove this integer part. Right. So for any real number x, you can find its closest integer, and then you remove the integer part. You just remove the lower function of x. Right. So if draw it you always be 0 or 1. So you take right. So for example, I take a square root of 2, which is 1.414. Right. So I go here or 0.4. And I find twice here, I get 828. And I do it again, but you will open. And mod 1 basically I go back to this side. So go back to this interval.
And if we have both a rational and an irrational part?
What do you mean? So everything is every real is either rational or irrational. Right? Every real number is either rational or irrational. If it's not rational, it's irrational.
I mean, if it has an imaginary part.
So this theorem have talked about this alpha to be a real. So I only care about the number. Yeah. So I take a real number and take a multiple. So in terms of this square root of version in this, what this theorem tell me is that if I take the fractional part of square root of n, and I take n from 1 to infinity, then it will become like very another number in this lower way. So what this Weyl theorem is that after this n goes to infinity, then it will uniformly spread from 0 to 1. if this number is irrational.
It makes some sense.
Yeah, it makes sense, right? But if you want to prove it's really uniformly, you need to split it out. And you need to use a Fourier analysis. And if you draw from a circle version, so circle version, that's you take the exponential of 2 pi I of it, and you draw you draw an angle. And then you will spread uniformly along the circle. 大家懂？就你拿一个物理数，你把这个物理数一直乘倍数，然后拿它的小数点出来，它的小数点会覆盖零跟一。就是你在任何一个零跟一之间都会找到一个数，你任何一个零跟 you take any number which is from 0 to 1, there exists some multiple of irrational number which is arbitrarily close to the number that you pick. It's fractional part. So so it makes sense that it will not be a period function because you don't have any period because it's irrational. But so non-trivial parts that it will make it uniform. Why this is important? Because that if I have this theorem, then I don't need to have continuous angle. Because you give me any continuous angle, as long as I can pick a face, if I can pick an irrational angle, then I can use this irrational, some multiple of this irrational angle to approximate arbitrary angle you give me. So then I can reduce the continuous to finite one. So this is the trick that why we have this equidistributed theorem. This is number theory too. And this is number theory theorem there. Very difficult. I mean, you can find proof or not. You can find it, but yeah. Okay, so simply speaking, so the thing you need to know is that if I have an irrational number, then I can times. Then this irrational angle can give or this. If you give me some irrational angle here, then I can find a multiple of this irrational angle such that you give me arbitrary angle here, then I can approximate this by multiple of some irrational angle. So this is the powerful tool. Okay, so simply speaking is that you use this T gate and X, the Hadamard gates, then you can create angle which is cosine theta divided by 2 equal to cosine squared pi over 8. Okay, so that so the proof basically you use some hard. Let's say you have X and Z location, and you just do this. It's going to minus I by X, I by Z, and then you calculate this. And you can just click it, and you will see the location. You will see this become a matrices, which is weird. But it has a rotation angle which is cosine theta divided by 2 equals to cosine squared pi over 8. And the result is saying that the result is that the solution of this equation, theta will be irrational. By the way, this is another non-trivial fact. The solution for this equation, theta will be irrational. I mean, if there's no square here, then theta is irrational. Yeah. Irrational 2 pi. Irrational multiple 2 pi. So if you have this angle, that means that you use Hadamard and this T gates. There exists some weird angle that you can do. You cannot do anything, any arbitrary angle, but there exists a weird angle, which is irrational multiple 2 pi. Once this is true, then you can use this angle and then do the multiple times. Then this will give you arbitrary angle, close arbitrary angle. So yeah, so this is schedule. So basically, if I want to approximate this R and alpha using this R and theta, then I can just pick some accuracy and pick a log n to be large enough. If we can be larger than 2 pi divided by delta, then that's by the Pinkel principle. I think everyone knows the Pinkel principle. Pinkel principle. So Pinkel principle was let me just. Okay. So let me just. Yeah. So the idea is that if let's say I from 0 to 1, right? Let's say I want the accuracy to be delta, so that means that I want to find the theta delta minus my theta, less than like 1/1000, suppose. Oh, sorry, less than 0. Then it's very easy that I just uniformly spread. I just cut this interval using length, let's say 2 pi divided by 0,000. Right. So I just make I just count my original interval with the difference with delta divided by 2,000. Then I use this theorem. I take my irrational angle, right? So my irrational angle from here to, and I take it twice, take it times 3, and I do a lot of them. And once the number of the multiple is larger than the number of interval, then by the conjunction principle, there exists twice. That there exists 2 different multiple, which inside the same interval. Yeah, so I mean, the details skip, but you can go back to the textbook. This is by the conjunction principle, there exists 2 multiples such that their difference is less than 0. Where each guy is a multiple of original weird angle. So this proves the results. Yeah, so I skip the proof. But idea is that if somebody gives you arbitrary unitary, forget about phase, then you can decompose it to arbitrary to you can decompose to arbitrary to number axis, this n. And for EW for each n R data, you can use some weird angle with multiple and approximate very close to this guy, very close to this guy, very close to this guy. And you combine 3 of them, you can prove that they're less than their differences. That Euclidean norms less than epsilon. So conclusion, which is I skip it, but the conclusion is that Hadamard and is however 8 approximately any single QB unitary to arbitrary angles. Oh. Yeah, I mean, so I just upload PowerPoint, but if you take this PowerPoint with the textbook, then you can prove that you can check the details. All right, so I just want to mention that there exists a more sophisticated decomposition compared to this using the Liard. There's a solving theorem. This is a theorem that if you're interested, you can go to find it. So this using what we do this unitary decomposition are somehow elementary. Right? We try to work down this proof using linear algebra, but there's a more sophisticated decomposition use the Lie algebra of this unitary matrices. Okay, so the final universality says that if I give you Hadamard, I give you phase gate and C naught, and this pi over gate, also called T gates, are approximately universal for all the quantum computation. So these are finite set. So it boils down. So what this is. So the final result is that you only need Hadamard and this T C naught. So these are single QB unitary. These are 2 QB. And these are enough to generate approximate arbitrary unitary. It feels amazing that you only need finite 3 of them. Yeah, so I skip this proof. Before let's see. Oh. Okay. So let me just talk about 10 minutes. So what we have done is the following, right? So we say that arbitrary unitary can be decomposed into bunch of this, bunch of. But what's the general unit? What's the number of this elementary guide to approximation? This is the question. So if you see the videos that I upload, there's a thing called Shannon theorem that prove that if you give me general like Boolean functions, and remember for the classical theory, then we have this Boolean function that one. Then so as I said that the number of functions here are double explanation because there are 2 to the n different n bit string, and each of n bit string can be mapped to either 0 or 1. So the number of s is 2 to the 2. So if you only give me m different so if you give me like some finite gate set, and but you ask me to use only m of them, then you can prove that. So if you like change, if you like you can only use up to n of them, then you at most get like d to the some number of, let's say let's say you have like 3 or 4 elementary. Well, whatever finite guy, you can only do like this guy up to power n different Boolean functions. So these are explanation, but these are double explanation. So by the counting arguments, then you can prove that most of the functions, most of the random functions require exponential elementary gates. So most of the functions are hard to compute by this counting argument. Okay. So that means that most of the functions you need to take exponential elementary gates to compute it. So this is a classical theory. And what I'm going to tell you is that in a quantum theory, this is also true. What we prove is that any unitary, in principle, can be decomposed using this finite guy. But most of the unitary takes the exponential elementary gates to approximate to get it. So most of the unitary are hard to compute. And so the problem is that how do you prove these results? Similar to classical one. So can any n to be unitary approximate efficiently by a polynomial sine circle? And the answer is no. Most of the unitary require exponential gates. So what this proof? What this proof is basically using the counting argument. So let me just quickly sketch the proof, and you can go back to the text to see it. So the idea is similar. Right? You ask how many quantum gates? How many quantum states are in the 2 to the n times 2 to the n Hilbert space? The answer is infinite, right? But we can constrain this space. So let me just talk about sketch, right? So let's say I have a G gates, G gate types, and each are acting on F qubits. Then you can prove that the choice per gate is n choose F, because you get n qubit gate, right? And each of them are at most F qubit, so you have n choose F times G, and which is density equal to n to F times G. Let's say you possible have different. Let's say so total state possible with n gates is n most. But the problem is that there are exponent. Let me see the problem. So in order to use this kind of argument, we need to somehow discretize this space. So let's say so I can cover n to b space, which is a unit sphere, a very large unit sphere with 2 to the n plus 1 minus 1 sphere that's attached with radius epsilon. So there's a unit sphere attached with small flow with radius epsilon. That's a little bit different. There's a picture. So which is this, right? You imagine that all the quantum states here are uncountable, right? But attached with this sphere with this small epsilon ball. And it just counts how many epsilon ball there. So the proof basically using a results that what's the what's the volume of n-dimensional sphere? And the result is that so you need to use the volume of n-dimensional sphere, and you can count the number of patches by compute the surface divided by the volume of the ball. And you can say, oh, I have these many quantum states, then I try to match the number, right? So basically the result is that the number of the patches is at least here. And this is the gates that you have. So in order for these two to match, you will prove that the number of gates M always is always. This is similar to the classical. Okay, so summary of this quantum circuit model. Summary is this. So in order for us to do this quantum circuit model, we need to have arbitrary to prepare state and computational basis. And we don't need to do we are not allowed to do arbitrary unitary now. We only have the elementary one. So we have the ability to perform some quantum gates. And the more precisely we can do with all of these. And also calling X, Y, and Z. But yeah, sorry, I later again. And especially only this H and C9 T are enough. Perform a measurement in computational basis. So this is the definition of quantum computation. The quantum computation is defined to be you can prepare state in computational basis, and then you are not allowed to do arbitrary unitary. You're only allowed to do alpha and C9 T with poly X, poly Y, poly Z, some elementary operation, and you can do the measurement. Okay. So the main question of quantum computation is that how this model compared to this circuit model. Is there a problem that you can solve with this model but not this circuit model? Oh, this is just one question, but there are extra questions. The extra question is that is this minimum? Is this minimum? Meaning that can I remove one of it? Then I still get a university. I mean, definitely I cannot remove C0, right? Because C0 is 2 qubit. If I remove C0, then everything will be single qubit unitary. So the problem is that can I remove one of this one? So for example, can I remove this T? I only use hotbar and C0.
We also have S, right?
Yeah, but it actually T.
Oh.
Yeah. So so the question is that can I remove T? If I remove T, is hotbar and C0 universal? Is okay. Okay, so let me tell you the answer. Answer is not. But if you go online, there are some people saying that the reason it's not, the reason why this is not universal is simple because hotbar is if you write in the computational basis, 1 square 2 x 1 1 1 x 1, and the C9 is just 1 0 0 0 1 0 1 1. And there are people saying that because they are not universal because there is no imaginary number here. Because hotbar real, right? Polar matrix element real, the C now all real matrix element. So there's no imaginary I here. So if I take, then it should not be universal. Because like for example, you take any complex number, let's say I here, this complex number cannot be approximated arbitrarily close to real numbers.
Right.
And technically, and then so one might say, so this is the reason why this is not universal. But it is the incorrect reasons for the quantum computation. So I will make a video recording to tell you that there actually in quantum computation, you don't need imaginary number. You can use extra 1 qubit to encode imaginary. So there are some deep reasons why Hadamard's not universal. And this is somehow out of the reach of this course, but yeah, I will mention in the video. Okay, so that's it.